take a look at this example. Would you change a channel? Now it says, kind of goes through and says, a survey found by this organization found that 45% of the people, if they were offended by a television program, they would change it, while 15% would turn off the television sets. And then it further stated that the margin of error is 3 percentage points and 4,000 adults were interviewed. So, how do these estimates compare with the true population percentage? What is meant by margin of error of 3 percentage points? And is a sample of 4,000 large enough to represent all the adults who watch television in the United States? What we're talking about in this lesson is confidence intervals. Basically, how confident can we be when we see data, we see these information saying, hey, 45% were offended, they change a channel. How confident can we be in those results? And that kind of just goes along with this. This is all estimation. When we say 1 out of 4 Americans is currently dieting, or 72% of Americans have flown on commercial airlines, the average kindergarten student has seen more than 5,000 hours of television, they're only estimates of true parameters. How do we know how true they are? Is there a way to even say how true they are? So what that leads us to is different types of estimates. We have a point estimate. Now it says a point estimate is a specific numerical value estimate of a parameter. That we've seen that word parameter before. And remember, a parameter is, we'll say it's a measure or characteristic obtained using all the data values in a population, and there's the key, population. When we're talking about parameters, we're talking about an entire population, a characteristic or a measure from the population, not a sample. And so it says the best point estimate of a population is the mean, of the population mean is the sample mean. So it says sample measures are used to estimate population measures. These statistics are called estimators. And for an estimator, we use the sample mean. And I know it's like just a bunch of words right now, so stick with me. But we use the sample mean. It's better than the sample median and the sample mode. So to be a good estimator, you should satisfy these 3 properties. Well, the first thing is you should be unbiased. You should be an unbiased estimator. The expected value of the mean of the estimates obtained from the samples of a given size is equal to the parameter being estimated. Okay, we've talked about that word unbiased before. The estimator should be consistent. So the second property is a consistent estimator. As the sample size increases, that value should approach the value of the parameter being estimated. Again, we're trying to get as close to the mean of the population as possible. And the estimator should be a relatively efficient estimator. Basically, it has the smallest variance. We don't want it to vary a lot, because then it's not going to be a true measure of the population. So all of this has to do with point estimators. But unfortunately, there's no way of really knowing how close the point estimate is to the population mean. Think about this. Okay, we can go through all this stuff, but is there a way that we'd know how close it is? Let me give you a quick example. Let's say a college professor wanted to get the average age of his students. So the average age of college students I'll try to spell correctly. And let's just say is 22.3 years. Okay, so that would be our point estimator. 22.3 years. But is there a way of knowing how dead on that is? How close to the actual population mean is 22.3 years? And there's really no way of finding out how close a point estimate is. Maybe our sample size was too small, whatever the case may be. We don't know. Maybe it's dead on, maybe it's not. So statisticians prefer instead the interval estimate. Because there's no way to know if a point estimate is exact, we want to work in an interval. Maybe have a better chance of the actual population falling in the interval. And it's the interval estimate of a parameter is the interval or range of values that is used to estimate the parameter, that measure we're getting from the population. It may or may not contain the value of the parameter being estimated. Okay. So instead of saying maybe that the average age of college students is 22.3 years, maybe we could say the average age is between 26.9 years and 27.7 years. Now, remember, when I gave you this example here, I said it was 22.3 years. Well, this is an interval estimate, and the estimate may or may not contain the actual value. So how can we be sure that, how confident we can be that if I wanted the average age of college students at a particular college, that it's going to fall between here? Well, if I wanted to say, let's say with 95% confidence, well, basically the more confident, the wider the interval. So what are we talking about? We talk about confidence. We're talking confidence levels and confidence intervals. The confidence level of an interval estimate of a parameter is the probability. Probability, kind of almost back to that standard normal distribution, the area, 100%, area under the curve. It's the estimate, the interval estimate will contain the parameter, assuming a large number of samples are selected. And we're going to talk later about how large that sample size has to be. Confidence interval is a specific interval estimate of a parameter determined by using data obtained from a sample and by using the specific confidence level of the estimate. Now, when we talk about the confidence interval, that's where we're going to say things like we are 90%, or with 90% confidence, or with 95% confidence, or with 99% confidence. And again, the higher, or the more confident we are, the wider that interval is going to get. So what we're going to do is we're going to focus on these confidence intervals to be able to make a statement saying, you know, we believe that with a 95% confidence, that mean is going to fall between these two numbers.